Today we're going to talk about transition metal dichalcogenides, also known as TMD or TMDC, about their properties and their synthesis and exfoliation methods and characterization. And the target of this talk is for those who are not very familiar with this kind of material, and those who are not working on the electronic and physics side of this material. So then let's get started. So first, let's talk about the composition of TMD. So from the name, you can tell that transition metal dichalcogenides is made of a transition metal, which we can choose from group 4 to group 10, and there are many choices, and the chalcogen element, which is sulfur, selenium, or tellurium. So this is the first big advantage of TMD over other 2D materials, because we have so many, a big library that is so big that we can choose whatever we want based on our application. And in this chart, it also summarizes some of the properties like the thermal stable phases in common conditions, if it's 2H or 1T, and also marks some of the properties like if it's metallic or insulating and semiconductive, and it also marks some of the very interesting physics phenomena like the superconductivity and topological phases. And among all these choices of transition metal, the group 6 transition metal TMD is of particular interest, and is most famous and mostly studied because, first of all, they are stable, and second of all, they have a tunable electronic and optical property that we will talk about later. And the group 6 material will be also the focus of this talk. So then let's start from the structure of the material. The left figure shows the structure of a 2H MOS2, where we can see a very clear layered structure. But within each layer, we have 3 atomic layers instead of 1, which is a carbon layer in graphene. So in TMD, we have 3 layers, which is a chalcogen layer, a transition metal, and another chalcogen. And between the big layers, it's connected by relatively weak van der Waals forces. And depending on the stacking order of these atomic layers, we can divide them into several different structures, or we can call phases. And 2 of the most important and common ones are the 2H phase and the 1T phase. So in the 2H phase, we can see within each layer, it's stacked like ABA and forms a trigonal prismatic structure. And this phase usually is semiconductive, while for the 1T phase, it's stacking like ABC. So it's more like octahedral structure, and this phase is usually metallic. And starting from the lattice structure, we can calculate the band diagram of TMD. And for example, this chart shows the evolution of the band diagram of a 2H MOS2. MOS2 is probably the most famous group 6 TMD of all the, among all the TMDs. And we can see from this chart that the red line is the conduction band, while the blue line is the valence band. And we can see very clear transition from an indirect, relatively small band gap to a direct, large band gap in the monolayer. And this is one of the reasons why we call it has a tunable property. That is because we have a tunable band gap depending on the composition and the layer number of this material. And this band diagram really affects the electronic and especially the optical properties of a material. And this is just one example where we show the photoluminescence, or we call the PL spectra of this 2H MOS2. And we can see this is for monolayer, bilayer, hexalayer, and bulk. And we can see because of the direct band gap of the monolayer, the PL intensity, or we can say the quantum yield, is very high for monolayer than other layers. So based on your application and your requirement, you can choose what number of layers you want. And one thing to mention is that this energy range is already in the visible light range. And in graphene, there's no such response in this range of wavelengths. So then we talk about some basic the property about the electronic applications of TMD. And just like other materials like graphene and carbon nanotube, TMD is also considered to be a potential candidate for future electronics and optoelectronics, because first, they're thin body nature, and second of all, they have a relatively high mobility, and third of all, they have a band gap, which is absent in graphene. So in this left figure, this is a very famous work where they use a single layer MOS2 to make a field effect transistor. And they got a very good IV curve with a mobility of 217, which is pretty okay for this kind of materials. And after this famous work, intense study has been done on like how to improve the performance of this kind of transistors. For example, in this work, they use a single wall common nanotube as the gate, and they got a very high ratio, which is also absent in graphene transistor because of the lack of the band gap. And they got a near ideal subthreshold slope of 65 millivolts per decade, which is near the limit of room temperature. And then, besides the field effect transistor application, there are many other very interesting phenomena, like, for example, ferromagnetism. In this picture, it shows a chemically exfoliated BSE2 monolayer, which is very large. It's pretty surprising. And in this figure, they measure the hysteresis loop of this material with an in-plane magnetic field at 300K and 10K. And we can see a very clear ferromagnetism behavior even at room temperature. And that makes this material, BSE2, has a potential application for maybe magnetic devices. And on the right, we show the coupled spin and valley physics, which is one of the focus in our research. So this figure shows the brilliant zone of a 2H monolayer TMD. And like I said before, the direct band gap is at the K points. And because of the symmetry, the K points can be divided into two groups, which we call the K valley and the minus K, or sometimes K prime valley. And we can see from this chart that the valence band spin splitting is actually valley dependent. And what's not shown here is that the optical selection rule for the circularly polarized light is also spin and valley dependent. So starting from this, there are many interesting phenomena, like shown here is a coupled spin and valley Hall effect, where if you apply an in-plane electric field in the X direction, then there will be a spin and valley current in the Y direction, and eventually there will be spin and valley polarization accumulated on the edges, very similar to the normal common charge Hall effect. And using this phenomenon, the 2H monolayer TMD has the potential for future spintronics and valleytronics. And there are many other interesting phenomena like superconductivity in, for example, RBSE2, and topological phases like the quantum spin Hall phases in 1T prime WT2. But those phenomena usually requires very low temperature. So then, although I'm not an expert in it, I gathered some information about the biomedical application related, biomedical related application. For example, on the left, they used I think it's PEG modified MOS2 nanoflowers to do like antibacteria experiments, and they used MOS2 plus hydrogen peroxide under near infrared irradiation. They found the antibacteria behavior to be quite efficient. And on the right, it shows a summary of some of the biomedical imaging methods that utilizes different properties of the 2D TMD. For example, in this work, where they used, I think, this photoacoustic tomography, they used the near infrared absorbance and the strong photothermal. The strong photothermal effects of TMD. And in here, CT, they use the high X-ray attenuation coefficient of TMD. So if you want to know more about it, maybe these references will be a very good start to start with. Okay, then let's talk about some selected synthesis and exfoliation methods to prepare thin layer TMD. So this slide summarizes some of the major methods that's being used to prepare thin layer TMD, either in liquid phase or non-liquid phase. And the choice of the preparation method really depends on your application, because for example, if you want to do in vivo measurements like in vivo experiments like drug delivery or in vivo imaging, then probably eventually you want some 2D material suspended in some kind of solution. Then the liquid phase fabrication method is probably better suited. While these methods are probably better for electronic and optoelectronic fabrication and for biosensors and gas sensors like we talked yesterday. So this picture shows the MOS2 thin layer prepared by electrochemical intercalation, which we will talk about later. And here the CVD MOS2 showing a very good 60-degree angles. And in here, this is the WSC2 monolayer and bilayer and bulk that's mechanically exfoliated from our lab. So then I choose some of these typical methods and explain a little bit more. For example, the chemical and electrochemical intercalation method is probably the most widely used method that's being used in the recent like 10 years to prepare TMD solutions in water or ethanol. For example, in here they used the weak van der Waals forces between the layers, and they show that some other molecules and ions can be intercalated in between these layers. For example, in this picture, they show the lithium ions, and they use the electrochemical setup to accelerate this process, and eventually you will get something like this. And after some other methods like ultrasonication, this structure is broken into this, and you will have very thin, nice little TMD flakes that's suspended in water or ethanol. And then the CVD is chemical vapor deposition. This is probably the most practical method for industrial synthesis of TMD, because first of all, it's cheap, and the second of all, it's easier for this method to be integrated into the existing industrial process. So this figure shows a very simple setup of CVD, where the sulfur and the molybdenum oxide reacts at a high temperature, and it was deposited on the sample. That looks like this. And this method is also shown to be able to create atomically sharp heteroless structures that looks like this. For example, they create a P-type WSC2 and N-type MOS2 heterostructure, and they demonstrate a PN junction that's made out of it. And this method can prevent any transfer methods that's widely used in other methods. So then lastly, we have the mechanical exfoliation method. This method is very simple, and it's probably the first method that's being used in 2004 to prepare graphene. And it's widely accepted that this method yields the crystal with the highest quality and fair size, a few microns to under maybe 100 microns. But the problem from this method is that it's random. It's a very random process, and the yield is very low. But as a starter, I think this is a very good starting point to experiments on the 2D material, and almost any kind of 2D material you want. And as requested by the organizers, I prepared a short video on like how to use mechanical exfoliation to prepare 2D materials yourself in the lab.
So mechanical exfoliation is probably the most straightforward and simplest way of getting layered 2D materials with almost any layer number you want. And the equipment you need is very simple. You just need a bulk material that looks like this, a tape, optical microscope, and a target substrate. It could be anything. It could be sapphire, it could be silicon dioxide, it could be any PDMS stamps or anything else. So as a start, we have this bulk material that looks like this. As we can see, it's already looks like a layered structure, which is pretty thin. But for exfoliation, we believe this is still too large and too thick. So usually what we do is that we peel off a smaller and thinner flake from this one. And we start with something like this, which is a few millimeters in size and looks much thinner than the original one. So then we have section of the tape. Here, this one we call it blue tape, which is not very adhesive comparing with the normal scotch tape. And we believe this is enough for exfoliation, and we don't need it to be that adhesive so that the residue can be reduced. We take this thin layer of material, bulk material, and then we put it on the tape. Very simple and lightly. And we do not want to touch it that much. Okay, so then we can either fold it or we can use another section of tape to do exfoliation. One sec. So what we're going to do is simply exfoliate it a few times. Like this, and you don't want to press it too hard. And you can see it's becoming like 2. And then we're going to do it again. And again. And again. It's still a little bit thick. You can tell the thickness of this layered material on the tape by examining its reflection under the light. Yeah, right now it still looks a little bit shiny, so I think probably one more time. This. Okay, now it's better. Okay, then we got the 2D material on the tape that looks like this, right? So then we're gonna bring the substrate that we want. For example, a silicon wafer that looks like this. Or, in our case, we prefer to use this PDMS stamp on glass, on cover glass. So you see the small rectangle in the center is a PDMS stamp, which is a organic material that's pretty soft and widely used. Okay, I'll put this back. Then we're gonna put it on the 2D material like this. And press it a little bit, not too hard. And then we cover it and put it there for example, 1 minute. Okay, now 1 minute has passed, and we're gonna peel it off like this. Okay, now we can see that. Let's cover it to prevent contamination. Now we can see that there's something, you can see it on the PDMS stamp. We're gonna put it on the optical microscope and look for it.
Okay, for example, this is one of the modular WIC2 I found on PDMS and on silicon and 125 nanometer silicon dioxide. And as you can see, the contrast for different substrates can be very different. So, for example, for ultra thin hexagonal boron nitride, it's very hard to see on PDMS because the contrast is really low. But on silicon dioxide substrate, usually it's visible. So the next step is if you are a starter or this material is new to you, then probably you want to do some characterization in the following step, for example, using the Raman or PL or AFM to determine the thickness and layer number of this material. And after you are familiar with it, you can probably just tell the thickness from the contrast, optical contrast under the microscope. And then the following step usually requires an extra step of high vacuum annealing under different temperatures depending on the stability of your sample. Okay, that's it. Thanks for watching. So the next section, we're going to talk about some of the characterization methods that we widely used for everyday research. So the first one is called the Raman spectra. So in the Raman spectra, we're actually using the laser to detect the lattice vibration modes, or we call the phonons, in a crystal. And in this left figure, it summarizes all the vibration modes for 2H TMD from bulk to modular. We can see we named all of the vibration modes, and some of them can be picked up by the Raman spectra. For example, in here, we picked the 2 peaks, which are called the E2G1 and the A1G peaks. And we can see the evolution from bulk to monolayer. And usually this method we can use first to determine the composition of the material, because the peak position of the Raman spectra can be used as a fingerprint of this material. And second of all, we can somehow determine the layer number using this method as well, as we can see in here. And also the peak position can be sensitive to other factors like strain, so it can be used to study the strain and other effects. And then if you're working on a 2D material with in-plane anisotropy, like in here, this is the distorted 1T WTE2, which has a very clear anisotropy. If you're working on that, then maybe you can use a polarized Raman spectroscopy to determine the orientation of this material. For example, if the polarization is parallel or perpendicular to this direction, then the Raman spectra will be very different, as you can see here. And then we talk about the photoluminescence, also known as the PL. So the PL spectra is usually can be taken at the same setup as Raman. But for this spectra, it's actually interacting with electrons and ions and excitons. So it has many things to do with the band gap. So as I said before, the transition of indirect band gap to direct band gap, and it's getting larger in 2H MOS2, really affects the optical properties of the material. And we can see from these figures, these are not MOS2, but very similar material, group 6 TMD materials. We can see because of the direct band gap of monolayer, the peak intensity of the PL spectra for monolayer is much bigger than the bilayer and trilayer. Note that these signals are actually magnified by these numbers. So for monolayer, it's much bigger, and the peak position also changes as well, because for bilayer and trilayer, these peaks are corresponding to the indirect transition, which has smaller energy than monolayer. So with this method, we can use it to determine the layer number, if it's a 1 layer, 2 layer, or tri-layer, very thin layer, very conveniently without having to do other measurements like AFM or anything like that. And this method is also used for determining the defect level and crystal quality of the material. But that usually requires an ultra low temperature, like cryo temperature photoluminescence. And then, of course, there are other methods that we can directly image the sample. For example, using electron microscope. This is the SEM image where we are capturing the information of the surface of the sample, and usually creates a very 3D look pictures like this. And this is the TEM and the STEM and the high resolution TEM and STEM images. And for these experiments, the resolution can be as high as like half an angstrom. So that means we can directly image the position of the atoms like this, which looks very cool. So this method can be used to detect the defects and the strain as well in this kind of materials. And of course, there are many other characterization methods, including like XPS, XRD, and for example, shown here on the right is the AFM image, where we can measure the height of the steps, which is also the thickness of the films. And we can check the surface roughness as well using this method. And on the left is something we call ARPS, angle resolved photoemission spectroscopy. This is a very interesting method because we can directly measure, this is the experiment, directly measure the band structure that looks like this. For example, this is a calculated band structure, and this is the experiment, and you can see it's very similar. And using this method, in this work, they even found the spin splitting at the K point, as shown here. This is K point spin splitting, and they found it in here as well. And as a conclusion, the characterization methods really depends on your requirements and your application, whether if you want to look at the defects, or if the crystal lattice structure changes, or if you want to see some other things, then you can choose between all these kind of characterization methods. And then, as a conclusion, TMD material has a tunable band gap, which gives them excellent electronic and optical properties, and there are many very novel physics phenomena in it. And as far as we know, the biomedical application is already widely studied, and you can probably start from one of the review papers that I listed before. And there are many different kinds of synthesis and characterization methods, and it really depends on your application. So thanks for listening. Yeah.
Thank you very much, Xintong, for your presentation. I'd like to open the floor for questions. Does anyone would like to ask a question? I believe not. Oh, we do. Yusuf?
Hi.
Hi.
Hi, this is Yusuf Waidi from Indian Institute of Science, Bangalore. So I have a few questions. The most important one that I have is this liquid exfoliation method, this liquid synthesis. So I'm having issue with the efficiency, like after everything, the percentage of the exfoliated nanosheet is very small. So how can I deal with that? Or what are your suggestions?
You mean the concentration of the TMD thin layer in solution, right?
Yeah, like I've gone through so many papers. So actually, there's from what I've seen, there's no like a direct protocol that one can follow. Everybody is having different protocol. So I don't know what is really responsible for this efficiency of a thing, because different people having different opinion, and then that is quite challenging for me.
Oh yeah, thanks for asking. But unfortunately, I don't work, and I never used this kind of liquid phase fabrication methods to prepare TMD. But I know that from the literature review, I think like different methods, like if you're using like solvent assisted method without this intercalation, then the ultimate concentration can be pretty low, and the efficiency can be pretty low as well. And as far as I know, this electrochemical setup like this is probably the fastest and yields the highest concentration of 2D material. But unfortunately, I never worked on this myself, so can't really answer your questions.
Yeah, thank you very much. The issue is that for biomedical applications, especially for the field that I am, I'm running away for this lithium compound, because it is quite difficult to be removed after the exfoliation thing. So that is why I'm using some kind of other solvent which are quite biocompatible. But the problem that I've been facing is this efficiency. So that is why I asked the question. Maybe you have some kind of suggestions.
Yeah, I don't think I have some suggestions, but other people from the audience, maybe if anyone has.
Do you have any suggestions? Because you do similar things with graphene. I know it's different, but how do you up your concentration?
We produce graphene by oxidation of graphite and then ultrasonication with a very high power sonication to obtain materials on the nanometric scale regarding lateral dimensions. I don't know if we can apply this to other 2D nanomaterials, probably, and that's something that I'm looking forward to testing in the future. So if it works, maybe I can tell you, and we can work together to produce the materials that you are interested in. So just email me, and that's something we can discuss in the future. Maybe we can set up a meeting to discuss that, because I'm also interested on achieving those materials with high yield, so that they can be used for biomedical applications. Maybe we can share our knowledge and do some progresses there.
Okay. So actually, I don't know who is talking, so I don't know how to contact you. If
I will share my email on the group chat. Okay.
And we also
thank you
have
very
time
much.
in the brainstorming session. Maybe
Exactly.
I can put you in the session with Dr. Turpint, and you can also speak there. I think, thank you, Yusuf, for your question. I think we also have a question from Rajendra.
Yeah, hi, Xintong. It's a nice talk.
Yeah, thanks.
I have a very quick question. Like you are discussing about a couple of methods for the exfoliation. So I know that MOS2 is having 2 phases, 1T phase and 2H phase.
Yeah.
Do you know that how to control the phase engineering using these methods? Like can we predict like using? I mean, I didn't directly work on the exfoliation, but I know the 2H 1T phase are different and they have different stability. Any comment on that?
Yeah, that's a super good question. Actually, the 1T phase is a metastable phase for MOS2, but it can be also pretty stable comparing with other TMD materials. And in my research, I never had this problem because I used the CVD MOS2 monolayers that is grown by the company or other groups, which is definitely a 2H, the 2H phase. Or mechanical exfoliation, which is from a 2H bulk material. So the result is definitely a 2H one. So the control of the phase, I'm not really sure how they did it in the chemically exfoliated sample, but I guess that if you're using for example, here, the electrochemical intercalation, which is another liquid phase kind of exfoliation method, then maybe it will follow the phase of the bulk material. But for the synthesis method, I'm not really sure how they control it. Maybe by controlling the temperature and pressure, because those are the key points of the phase transition.
Thank you. And just a small query that you are showing polyethylene glycol MOS2, a functionalized MOS2 at some point. And is it a chemically exfoliated CVD? I mean, so MOS2 or CVD here? This MOS2, how did you prepare? Is it mechanically or CVD method to get this MOS2? Yeah, the precision MOS2, yes.
This one, I think they used the chemically exfoliated sample because they're seeing solution. The CVD usually don't create things in solution, because for CVD and MB and other methods, usually the result is not soluble.
They were solids. Yeah, I understood. But do you know what is the phase of this MOS2 at the 2H phase or a 1T phase? This
one, I think it's 2H, I think.
Okay, good. Thank you. Yeah, I mean, that's it from me.
Yeah. Thank you. We just have one more question in the chat, and then I want to introduce our next speaker. So I got this question, and the question is, for the Raman spectra for MOS2, what does it mean when the two peaks range from 379,404 instead of 384,410? I can also put it here in the chat for everyone. Not that.
Okay, you mean the position of the peaks, like in here? I think first of all, let me see the numbers.
There you go.
Instead of this is a very common phenomenon that we observed in our research, and usually between our even in this on the same sample, sometimes we can have a Raman peak shift of like this range of a few centimeter to the order of -1, and this is quite common. I think the first probability is because of the electron structure is a little bit different in these kind of materials and on different positions of the sample as well. And there might be some kind of intrinsic strain or anything like that, but this is very normal. Yeah, and we have no idea how to like prevent it from happening every time. Yeah.
Perfect. I hope that answers the question to whoever asked, but if not, we'll have more time in the brainstorming session. So thank you so much, Xintong, for your presentation.